thermodynamic potentials and Maxwell's equations. Okay, what's our new lesson or the first lesson in the unit 2? Unit 1 is already over, 2 lessons are over. Now we are going to start the first lesson from unit 2, that is thermodynamic potentials and equations. Right. Here we are going to study about the potentials, that two thermodynamic potentials. You know the word potentials from mechanics. In mechanics, we always use the term or the physical quantity called potential. Okay, that is the mechanical potential. Here, the potential we are referring to is called as a thermodynamic potential. Thermodynamic potential. Right here, before going to these potentials, okay, we have to define some functions here. There are different functions. See, based on the equations of these functions, we are going to have the Maxwell's relations or Maxwell's equations, right? Here, yeah. So that's why we call this lesson as a thermodynamic potentials and Maxwell's equations, right? Here, you know about the parameters of a thermodynamic system, pressure. Okay, thermodynamic system is characterized by pressure. These are the parameters which describe a thermodynamical system. Next, volume. Okay. Next, temperature, P, V, T, and also entropy. These are all the parameters which describe any thermodynamical system. See, if you consider any two from these four variables, okay, they are independent. Okay, you can form the set of any two such parameters as a independent variables. Okay, rest of the two variables will be the dependent functions. Dependent functions. So out of these four parameters, any two are okay independent. Rest of the two are dependent. Okay, that depends upon the previous functions. Okay, which are already considered. So what do you understand from this? There exists a certain relation between these four parameters. You may define or you may describe two parameters in terms of the other two parameters. Okay. So by this you can understand that there are certain relations between thermodynamic variables. If you take law of thermodynamics, see what is first law of thermodynamics? dq is equal to du plus p dv. So how many parameters you are using? P and D. From these four parameters, you are using two parameters P and V. Okay. Next, if you take the second law of thermodynamics, that is dq is equal to TdS. This follows from the definition of the entropy. ds is equal to dq by T. So dq is equal to TdS. Okay. Here also, we are using two parameters from these four parameters T and S. Here in the second law we are using two parameters called T and S. T and S. Okay, so in this way, two independent parameters are necessary to describe any thermodynamical system. Okay. See, these are the relations which describe a thermodynamical system. But only such two relations are not enough to describe any one thermodynamical system. Okay, some more relations are needed. Okay, now we are going to study about those other relations. Okay, in terms of these parameters P, V, T, and S. Right. Here, some variables were already considered on P, V, T, S. Some functions of these P, V, T, S are known as the thermodynamic potentials. See, the functions of these parameters are known as the thermodynamic potentials. Okay. The functions of these parameters are known as the thermodynamic potentials. Okay. Now we are going to define them. The functions of these parameters are called as thermodynamic potentials. So the functions of pressure, volume, temperature, and entropy are known as the thermodynamic potentials. Okay. So that means these potentials are expressed in terms of these four parameters, right? What are they? Here I am going to give you the names of the thermodynamic potentials, which in turn expressed in terms of these four parameters. What are they? See, internal energy, one. Internal energy, this is U. Okay. See, these are all the functions of our four variables PVTS. It means pressure, volume, temperature, and entropy. Okay. So, what are the examples of thermodynamic potentials? Internal energy. Next, free energy. Free energy. It is denoted with the letter F. Next, what are the other thermodynamic functions? Next, third, enthalpy. Enthalpy. We denote this with the letter H, capital H, enthalpy or total energy function or total heat function, right? Enthalpy. Next, Gibbs function, GIBB. Gibbs is the name of the scientist. Gibbs function. Okay. G. See, we are calling these potentials to be functions. Why? Because these are depending on some other parameters. Okay. So, what are the thermodynamic potentials? Internal energy is one thermodynamic potential, and free energy is also one thermodynamic potential, and enthalpy, H, and Gibbs function G are also called as the thermodynamic potentials. These four thermodynamic potentials are the functions of these independent parameters from the set of pressure, volume, temperature, and entropy. Temperature and entropy. Okay. That means you may express all these functions in terms of these parameters PV, TS. PV, TS. Now, we are going to define these thermodynamic potentials one by one. First of all, we are going to study about this internal energy. Next, we discuss about the free energy. Next, we discuss about the enthalpy. And next, we discuss about this Gibbs function. See, actually, the first thermodynamic potential called internal energy is already familiar to you. You know about this. Why? Because in the first law, there is this U, parameter U. Okay. So it is the known thermodynamic potential, of course, but we are now again going to study this internal energy. Even though we are familiar with this internal energy in the first law of thermodynamics, again we are going to study about this as a thermodynamic potential. There we did not notice that it is the thermodynamic potential. Okay. Now we are noticing this internal energy to be the thermodynamic function which depends on any two from the set of four parameters PVTS. Right. What is internal energy? Internal energy, this energy can be possessed by virtue of its molecular motion. See, what is internal energy actually? What is internal energy? Actually, we studied about this internal energy previously. What is the definition? This internal energy is equal to the sum of the potential energy and kinetic energy of the molecules. Okay. Molecular constitution, positions of the molecules as well as the motions of those molecules. Okay. These two things are contributing to the internal energy of the system. Okay. So you can get the definition of this internal energy by the first law of thermodynamics. Right. See, whenever the system goes from one state to other state, okay, its internal energy does not depend on the path. Okay, suppose that your system is at state A initially. Finally, it is going to the state B. See, from A to B, you can take the system through so many paths. Okay, by doing different operations, you may transform the gas from position A to position B. There are so many ways to reach another position. But here, the internal energy describing the system does not depend on the path. Okay, whether you are taking the system from path 1 or from path 2 or from path 3, this does not matter. Okay, the internal energy U depends on only this initial point and final point, but not the way through which you reached from state A to state B. Okay. If you are again bringing your system to the same point A, You are taking your system like this, and again you are bringing your system to the same position A. Then what happens to its internal energy? As long as there is no net change in the state of the system, then there will not be any change in its internal energy. Okay, initial point is the same and final point is the same. In that case, internal energy is constant. It does not change. Again, you are bringing the system to the same position A. That means there will not be any change in the internal energy. These are all the properties of the thermodynamical function, thermodynamic potential called internal energy. Called internal energy U. Okay. Why? Because whenever you try to change the state of the system. Suppose that you are taking some gas inside the cylinder and you are heating that gas. Then what happens? All the positions of the gas molecules will be changed and the kinetic energies of gas molecules will be changed. That's why the internal energy of the gas also changes. But whenever again you are pulling the gas to the same state, then what happens? Again, all the molecules come to their own positions and they reach their own initial kinetic energy. That's why there will not be any change in the internal energy of the system. That you have to note. So, internal energy is only the function of initial and final positions. That you have to note. For a complete cycle, there will not be any change. Okay. In any cyclic process, the internal energy will be constant. Okay, how to get the formula for the change in the internal energy from the first law of thermodynamics? See, I am writing first law of thermodynamics. dq is equal to du plus dw, or say pdv. This is the first law. Now I want to find the equation for the change in internal energy. Okay, we are talking about this only now. So from this first law of thermodynamics, what will be this du is equal to, you take this pdv to this side, then what happens? Du is equal to dq minus pdv. Okay, this is what the expression for du. If again you are using the second law, from second law just now I wrote dq is equal to tds. Why? Because ds is equal to dq by t. That is the definition of entropy. Definition of the entropy can be treated as the equation of the second law of thermodynamics. Okay. So whenever you use this relation in our previous relation, what happens? Du is equal to d in the place of dq, you put tds minus pdv. Yeah. Now you express du in some particular form. See, first term is very much similar to the second term. First term is very much similar to the second term. TDS minus PDV. Right? See, here it is expressed in terms of P. Okay, PV and T and S. Okay, PVT. Yes. It is expressed in terms of these parameters as I just now told to you. Okay. Whenever you put second law, du is appearing to be depending on all the four parameters. Okay. Otherwise, you notice that du is equal to dq minus pdv, means you thought that this du is a function of a p and v only. Okay. Right. Now, By making use of the last equation, you may write, see, dou u by, suppose that you are integrating, you are doing partial integration, a partial differentiation with respect to the entropy. See, there are two variables, ds and dv. So you may now integrate this entire equation with respect to either ds or dv. Whenever you differentiate this du with respect to ds at constant volume. Now I am assuming that v is a constant. Then what happens? You see the first term? T ds is there. Dou s by dou s. Okay, here you are not going to get anything. 1. Differentiation is 1. Minus, what about this? P dv is there, but I am considering this differentiation with respect to s at constant volume. So this will be 0. dv will be 0. So you are going to get one equation here. What is that? Dou u by dou s at constant volume is equal to what you are getting on this side? Only t. Okay. Now you write down all these things. Now once again you try to differentiate this thermodynamical potential with respect to V at constant entropy. Then what happens? Yeah, here I am doing. See, now I am differentiating the same equation with respect to V at constant entropy. Dou u by dou V with respect to constant entropy. Now what about this first term? At constant entropy, T ds means 0 minus P dou V by dou V. With respect to V, we are doing differentiation. This is 1. So here, what's your equation now? Dou U by dou V at constant entropy is equal to T into 0 is 0. 0 minus P into 1 is just minus P. So here you are going to get the equations for two things, temperature and pressure. Okay. Now, if you take here, you do one more differentiation here. Dou U by dou S into V, you differentiate this dou U by dou S, first equation, with respect to V. Okay. Next, you differentiate this dou U by dou V, dou U by dou V with respect to dou S. See, you are going to get the same expression on one side. On one side, let us see now. Now I am writing these last two equations together with each other. See, I am writing this first equation here, dou U by dou S. See, dou U by dou S at this one first equation is equal to T. Okay. Now we got these two equations starting from the first law, that is from the definition of thermodynamic potential called internal energy. With the equation of internal energy, we arrived these two equations. Okay. I am retaining only these two equations now. Again, here we are going to redifferentiate these two expressions. Yeah. Here, You see here, what is the equation for du? Du is equal to TdS minus PdV. So from the definition of perfect differentials also you can write this equation. Otherwise you simply uh, differentiate this equation with respect to V. First one. Okay, you differentiate first equation with respect to this V. Dou by dou V of dou U by dou S at constant volume is equal to, you are differentiating with respect to V na, dou T by dou V. Dou T by dou V. Right. Now, here, next, here you are differentiating with respect to V means, which is constant here? Yes, entropy is constant. Next, take the second equation. You differentiate this equation with respect to ds on both sides. Dou by dou S, dou U by dou V at constant entropy is equal to, on this side you are having minus P na, minus dou P by dou S at constant volume. Why? Because you are differentiating with respect to entropy. You see here, according to the chain rule in the differentiation, you see this thing is equal to this thing. Why? Just there is a change in the order. Okay, these orders in differentials can be interchanged. Then what happens? This LHS becomes to this LHS. Both are same except the order. But the order can be ignored by using the rules of the calculus. Rules of the calculus. So what you are going to get, whenever two LHS values are equal, then RHS values also should be equal. That means this one is equal to this one. I am going to write that now here. What is that? First RHS is equal to second RHS. Dou T by dou V at constant entropy, this thing is equal to this thing. What is that? Minus dou P by dou S at constant volume. Now this is called as the first Maxwell's equation. This is called as the first Maxwell's equation. How you are arriving this first Maxwell's equation? Starting from the definition of the internal energy, you are going to derive this first Maxwell's equation. Here I am writing, this is called the, this is called first Maxwell's equation. This is called as the first Maxwell's equation. Okay. On one side index is S, on the another side index is V. Okay. This is what the Maxwell's first relation, first equation. Okay. If you go for the next thermodynamic potential, then you are going to get another Maxwell's equation. Okay. If you want to get the second Maxwell's equation, you have to start with the definition of a free energy function, free energy F. Okay. So next we have to define free energy and we have to follow the same procedure in order to get the Maxwell's equation. Okay, first of all, let us try to define this free energy. Okay, what is next thermodynamic potential? Second one. You have to remember them in one particular order, then only you will be able to get the equations in one particular order. Free energy. What is the symbol for it? F. Yeah, uh, you start from the first def equation of the du only in order to get the formula for f. Just now we wrote that du is equal to TdS. This is a combination of first law and second law. No? Just now we wrote this equation. Okay, I am using this equation in order to find the equation for thermodynamic potential F. Thermodynamic potential F. Here, yeah, you consider, okay, a process in which the system exchanges heat from its surroundings. Suppose that one system is allowed to exchange heat with surroundings. That means it is not adiabatic. Then what happens? It is able to maintain the constant temperature. So we are considering an isothermal process, okay, taking place in the system. Then T is constant now. In that case, okay, for an isothermal process, TdS can be written as d of Ts, isn't it? How? D of Ts, you may write TdS as d of Ts. Since T is constant, again you are going to get TdS. Since T is constant, you are taking it outside, you are just differentiating ds. So TdS is equal to just d of Ts for an isothermal process. For an isothermal process, right? Now I am going to use this in the above equation. Therefore, your du is equal to, instead of TdS I am writing d of Ts minus of this PdV. Right. Now you take this TdS to this side. Then what happens? du minus dTs inside the bracket is equal to minus PdV. Actually, what is PdV? It is the expression for work, dW. So this is minus of dW. PdV means dW. See here, du minus dTs means you take d common. Here you are going to get u minus Ts inside of this bracket. Isn't it? It is very clear. D of u minus Ts is equal to minus of dW. What is such a quantity u minus Ts? This is called as free energy function. Free energy function. Suppose that I am going to write this last equation as d of, instead of something which is inside the brackets, I am writing f. This is equal to minus dw. In my opinion, what is f? Where f is identically equal to u minus Ts. Why? Because in the place of u minus Ts, I am writing some another function f. Isn't it? Yeah. Here, such a function is called as a thermodynamic potential called free energy. So, what is the definition of free energy? Okay, see, it is equal to, that means it is work done on the system. See, on this side you are having W. Okay, work done on the system means, yeah, if you take this as positive, on this side you get minus. That means decrease in the Helmholtz function. You see here, I am writing this. I am erasing all these things now. If you take plus, if you multiply on both sides with minus, then what happens? You are going to get minus df. See, dw is the work done on the system is equal to decrease in the free energy. See, what happens when you do some work on the system? What happens? This here, the free energy of the system decreases. So, the work done on the system is equal to the decrease in the how much work you have done on the system, that is equal to how much free energy is decreased. Okay, this is what the definition of free energy. Okay, df is equal to minus dw, or dw is equal to minus df. This is going to give you, okay, the definition of the thermodynamic potential called free energy. Okay, how to define this? The energy function is one such a function, the decrease of which always gives the work done on the system. This is what the definition of the free energy. Definition of the free energy. Okay, right. This is about the free energy. Okay, yeah. From based on this, okay, if we based on this, we may write the second Maxwell's equation as well. Second Maxwell's equation as well. Okay. Now, okay, we're almost, I think, running out of time. So it is better to derive this relation in the next class. Okay.